Welcome to our deep dive today. We're going to be looking into the vulnerability of continual learning neural networks to targeted data poisoning attacks.
Okay.
We're going to be focusing on a research paper
Excellent.
titled Targeted Data Poisoning Attacks Against Continual Learning Neural Networks
Great.
by Huayu Li and Gregory Ditzler from the University of Arizona.
Interesting.
So this paper is pretty fascinating. It really digs into how these attacks can kind of exploit the very nature of continual learning
Right.
to manipulate AI systems.
Mm-hmm.
So let's just start with like a quick overview
Yeah.
of continual learning itself.
So continual learning is kind of a critical subfield of machine learning
Yeah.
that involves training models on a stream of data that's presented sequentially.
All right.
And the aim is to enable the models to adapt to new information without forgetting previously acquired knowledge.
Yeah.
Kind of like the way humans learn.
Like how we do it.
Yeah.
And this is where catastrophic forgetting comes into play, right?
Mm.
It's the exact.
This is like the challenge.
Yeah, catastrophic forgetting is a big challenge in continual learning,
Uh-huh.
where a model tends to forget or overwrite previously learned information
Yeah.
when exposed to new data.
Right.
This poses a hurdle
Makes sense.
in developing truly adaptable AI systems.
So the researchers in this paper, they really focused on the vulnerability of the regularization-based continual learning methods
Yeah,
to these types of attacks.
right.
Why regularization-based methods particularly?
So regularization-based methods, things like elastic weight consolidation, or EWC, online EWC, and synaptic intelligence,
Okay.
they offer a memory-efficient approach to continual learning
Yeah, that's it.
because they don't require storing past data.
Okay.
Instead, they employ regularization techniques
Okay.
to protect crucial weights from drastic modification during new learning.
So like they're making it more efficient,
Yes.
but that also makes them more vulnerable.
But that reliance on regularization,
Uh-huh. Makes them kind of a prime target for manipulation.
so the attackers are kind of exploiting that efficiency
Yeah, that's right.
in a way.
The researchers demonstrate how a targeted data poisoning attack can be strategically used
Oh, okay.
to induce catastrophic forgetting in these models.
So can you go a little deeper into what a targeted data poisoning attack is,
Sure.
especially within like the framework of adversarial machine learning?
So adversarial machine learning
Yeah.
explores the vulnerabilities of machine learning models to intentional manipulation.
Uh-huh.
And in the context of this paper,
Right.
a targeted data poisoning attack occurs during the training phase,
Okay.
where malicious actors inject carefully crafted data
Yeah.
into the training set to force the model to forget specific tasks.
So it's not just about disrupting like the overall performance,
Right.
but really strategically targeting
Yeah.
like specific aspects
Yeah.
of the model's learned knowledge.
The attacker's goal is to make the model forget a specific task, making it a type of availability attack.
So the paper mentions a white box attack scenario.
Yeah.
What does that mean?
A white box attack scenario implies the attacker has complete knowledge
Okay.
of the model being targeted.
So they have access to like everything.
Yeah, this includes the model's architecture, parameters, the training data for the new task,
Okay.
and even the data set of the task that they want to be forgotten.
So it's kind of a worst case scenario from like a security standpoint.
Yeah, you could say that.
They're working with complete information
Yeah.
about the system that they're attacking.
Uh-huh.
Another term that's used in the paper is clean label attack.
Right.
What does that mean?
A clean label attack refers to a scenario where the attacker can inject
Oh.
poison samples into the training data,
Okay.
but they can't change the original labels
Oh.
associated with those samples.
So they can't like mess with the labels, but they can mess with the data.
Yeah, this makes the attack much more subtle and difficult to detect
Interesting.
as the poison data seemingly appears correctly labeled.
So it's more covert.
It's a covert manipulation of the data itself
Right.
without raising any red flags.
Like without mismatched labels or something like that.
Exactly. It's about finding ways to
Yeah.
make the poison data blend seamlessly
Yeah.
with the clean data,
Gotcha.
thus making detection a challenge.
So the paper explores how these poison data points are crafted
Right.
to induce the desired forgetting.
Uh-huh.
So let's get into that.
Yeah.
How do the attackers like achieve this manipulation
Okay.
without altering the labels?
So the attacker aims to exploit the way that the model learns from data during training.
Okay.
Imagine if the attacker could simply flip the labels
Right.
of the target task data
Uh-huh.
and inject it into the new training set.
Yeah.
This would confuse the model and induce forgetting.
That makes sense, but they can't do that.
Right.
It's a clean label attack setting.
Right. So they need a different approach.
All right.
Instead of directly flipping labels,
Yeah.
they aim to craft poisoned data for the new tasks in a way that mimics the effect of flipping labels.
Gotcha.
They do this by creating poisoned data whose gradients during training
Yeah.
approximate the effect of those flipped labels.
Interesting.
It's like creating a false memory
Yeah.
that overrides the original learning.
So they're not manipulating the label, they're manipulating the data.
Precisely. They're manipulating the data itself
Yeah.
to create a similar effect
Right.
on the model's learning process.
Sure.
To achieve this,
Uh-huh.
they introduce algorithm 2,
Okay.
a method to generate these poison samples.
So let's break down algorithm 2.
Okay.
How does it work? Can you walk us through the key steps involved?
So algorithm 2 leverages the concept of momentum
Okay.
and gradient calculations
Yeah.
to iteratively craft the poison samples.
Oh.
So initially, the poison samples are simply the clean samples from the new task.
Okay.
Then the algorithm calculates the gradients of the model's parameters
Yeah.
with respect to a batch of data from the target task.
Uh-huh.
This acts as a reference point for how the model learns the target task.
So they're like establishing a baseline.
Yes, you could put it that way.
They're understanding how the model learns this specific task
Yeah.
that they want it to forget,
Uh-huh.
and then they do what?
Then they enter an iterative process.
Okay.
In each iteration,
Yeah.
they calculate the gradients of the model's parameters
Right.
with respect to the current batch of poison samples.
Gotcha.
These gradients are then compared with the reference gradients calculated earlier.
Uh-huh.
The goal is to make these two sets of gradients as similar as possible.
So essentially, like,
They essentially want the model to treat the poison data
yeah.
as if it were data from the target task,
Right.
even though it isn't.
Okay, so how do they do that?
To achieve this, they utilize a momentum term
Okay.
to guide the direction of the perturbations
Yeah.
added to the poison samples.
So the momentum term is used to kind of nudge the poison data in the right
Certainly.
direction.
It helps the algorithm find the optimal perturbations
Mhm.
that effectively mimic the gradients
Okay.
that would have been generated if the labels were actually flipped.
Gotcha. So now we understand how these poison samples are generated.
Right.
How effective is this attack in practice?
Okay.
Like, what kind of experiments did the researchers conduct to test this?
To evaluate the effectiveness of their attack,
Yeah.
the researchers used two data sets, rotated MNIST
Okay.
and MNIST fellowship.
Right.
Rotated MNIST is a domain incremental learning scenario
Okay.
where each task involves classifying digits that have been rotated by a different angle.
So they're all digits,
Yeah.
but they're just oriented differently,
Yes.
and that's the task.
Yep. This tests the model's ability to recognize digits regardless of their orientation.
Gotcha.
MNIST fellowship, on the other hand,
Yeah.
is a task incremental learning scenario.
Okay.
It combines 3 different MNIST variations. Original MNIST for digit classification,
Right.
fashion, MNIST for classifying fashion products,
Okay.
and KMNIST for handwritten characters.
Okay.
This presents a more diverse set of tasks,
Gotcha.
and it challenges the model's ability to retain knowledge
Okay.
across different domains.
So it's testing its ability to, like, switch between tasks
Yeah.
without forgetting the other one.
To ensure a fair comparison,
Right.
both the attacker and defender models
Wow.
use the same architecture. A multi-layer perceptron, or MLP,
Right.
with 2 hidden layers and ReLU activation functions.
Right. So they're controlling for that.
Yeah, this creates a controlled environment
Right.
to isolate and assess the attack's effectiveness.
It sounds like they designed a very rigorous testing ground for their attack.
That's right.
So did it work?
They wanted to ensure that the results accurately reflect the attack's potency,
Yeah.
independent of model architecture differences.
Okay.
Now let's delve into what they discovered.
Okay.
Tables 1 and 2 in the paper
Yeah.
present the key findings from their experiments.
And what did those findings reveal?
So the results clearly demonstrate that the attack effectively reduces
Okay.
the accuracy on the targeted task
Right.
as the percentage of poisoned data increases.
Interesting.
For instance,
Yeah.
Table focusing on the MNest Fellowship dataset,
Right.
shows how the accuracy on task 1, the target task,
Yeah.
drops significantly for all 3 continual learning algorithms.
Sure.
EWC, online, EWC, and SI,
Okay.
as more poison data is injected into tasks 2 and 3.
So as the model's exposed to more poison data,
Right.
its memory of the target task
Yeah, that's a good way to put it.
deteriorates.
Interestingly, Table 2 shows that EWC appears to be more robust in the domain incremental learning setting.
With rotated MNest?
So there's a difference there.
Yeah.
Between the two.
The researchers suggest that EWC's use of a separate Fisher information matrix for each task
Okay.
might be a factor.
Interesting.
This matrix helps EWC estimate the importance of different weights for each task,
Okay.
potentially offering some protection
Gotcha.
against drastic shifts in the model's parameters
Okay.
that would lead to forgetting the target task.
So it still has some, like, built-in resistance?
Yes, it suggests that certain algorithmic designs
Yeah.
might offer inherent defenses against such attacks.
So it's not completely vulnerable, but it's more vulnerable
Yeah.
than the other one in this particular scenario.
Now, moving beyond tables,
Okay.
Figure 4 provides a visual representation of the attack's effectiveness.
Okay.
It shows how the error on the targeted task
Yeah.
steadily increases
Uh-huh.
as the percentage of poisoned data increases.
So even small amounts
It clearly demonstrates that even small amounts of poisoning
can significantly impact the model's performance on the targeted task.
Okay.
It highlights the insidious nature of this attack,
Right.
slowly chipping away
Yeah.
at the model's knowledge.
So the paper also examines
Yeah.
the stealth and efficiency of this approach.
Right. Because, of course,
Because if it took forever to do it.
an attack that's easily detectable
Yeah.
or takes forever to execute
Right.
wouldn't be very practical.
Yeah, exactly.
yeah.
It wouldn't be much of a threat.
To address this,
Yeah.
they used TSNE visualization in Figure 5
Okay.
to show how difficult it is to distinguish
Right.
between the poisoned data points
Hmm.
and the benign ones.
So you can't even, really tell by looking at it.
The poison samples blend seamlessly with the clean data,
Right.
making detection quite challenging.
So even if you were to, visually inspect the data,
Precisely.
it would be hard to tell.
And to add to that, the poisoning process itself
Yeah.
is computationally efficient, requiring minimal time to generate a batch of poison samples.
Interesting. So it's quick, too.
It suggests that this attack could be deployed
Yeah.
relatively easily and quickly.
So that makes it like a very, very potent threat.
This combination of effectiveness, stealth, and efficiency
Right.
makes this a truly concerning vulnerability.
Yeah, it really underscores the need for...
It underscores the need for robust defenses
Yeah.
against these types of attacks,
Yeah.
especially as continual learning models are being implemented
Right.
in more and more real-world applications.
Right. And their security is paramount.
Their security is paramount.
Given their increasing role in critical tasks.
Given their increasing role
Yeah.
in critical tasks.
This has been a really interesting deep dive.
Yeah.
It's given us a lot to consider.
Huh.
Let's continue exploring this in
Yeah.
our next segment.
Sounds good. All right. Picking up from where we left off, let's delve a little further into the paper's exploration of the attack's effectiveness across different continual learning algorithms and datasets.
Yeah, let's dive into those details.
Yep.
So they conducted experiments, right, with 3 popular regularization-based algorithms,
right.
EWC, online EWC, and synaptic intelligence, or SI.
These algorithms represent distinct approaches within regularization-based continual learning,
Right.
making them a good test bed for assessing the attack's effectiveness across different methods.
And they tested these algorithms on the 2 datasets we talked about earlier.
Yes.
Rotated MNest and MNest Fellowship.
These datasets provide diverse learning scenarios, domain incremental and task incremental,
Right.
allowing for a comprehensive evaluation of the attack's impact.
So the paper presents its findings in tables 1 and 2.
Right.
Can you walk us through the key observations from these tables?
Table I focuses on the MNest Fellowship dataset,
Okay.
a task incremental learning scenario. It shows that as the percentage of poison data increases the accuracy on task 1, the targeted task drops significantly for all 3 continual learning algorithms: EWC, online EWC, and SI.
So the takeaway here is that the attack is achieving its objective
Precisely.
of degrading the performance on that specific task that it's targeting.
Now, Table 2 focuses on the rotated M&ES dataset,
Okay.
which represents a domain incremental learning scenario.
Yeah.
Here, we see a slightly different trend.
Good.
While the attack still effectively reduces accuracy on the targeted task as the poisoning rate increases.
Right.
There's a notable difference in the robustness of EWC
Interesting.
compared to online EWC and SI.
So is this where that idea that EWC might have some kind of inherent resistance mechanism
They do.
comes into play?
In the rotated MDS setting, EWC exhibits a higher resilience to the attack compared to online EWC and SI.
Okay.
This observation aligns with the researchers' hypothesis that EWC's use of a separate Fisher information matrix
Right.
for each task provides a degree of protection against drastic parameter changes
Okay.
that lead to forgetting.
So while not entirely immune, it does seem like
That's right.
EWC offers a little bit better defense.
It highlights the importance of considering algorithmic design choices
Yeah.
when evaluating the vulnerability of continual learning models to these attacks.
Okay, so moving beyond the tables, the paper also includes visual representation of the attack's effectiveness
Right.
in Figure 4.
Figure 4 visually reinforces the findings from the tables.
Okay.
It plots the error on the targeted task against the percentage of poisoned data.
Uh-huh.
As the poisoning rate increases,
Yeah.
the error on the targeted task steadily climbs for all three algorithms and across both data sets.
So this really drives home the point that
It helps to emphasize
these attacks can be really, really effective.
the severity of this vulnerability.
Even when the amount of poisoned data that's introduced is relatively small. Now, besides the attack's effectiveness, the paper also looks into its stealthiness,
Yes.
which is, of course, crucial for real-world applicability.
Because an attack that's easily detectable wouldn't pose a significant threat.
Right, exactly.
To assess the attack's stealthiness,
Yeah.
the researchers use a technique called TSNE visualization,
Okay.
as shown in Figure 5.
Hey, can you explain how TSNE visualization works?
So TSNE is a dimensionality reduction technique
Okay.
that allows us to visualize high-dimensional data
Yeah.
in a lower dimensional space, typically 2 or 3 dimensions.
So they're essentially trying to see if the poison data, visually stands out from
Right.
regular data.
Figure 5 clearly shows that the poisoned data points are remarkably difficult to distinguish from the clean data points.
Wow.
They are interspersed throughout the visualization, effectively camouflaged.
So you can't even tell by looking at it
Exactly.
that the data's been poisoned.
This finding reinforces the stealthy nature of the attack, making it even more challenging to defend against.
And on top of that, the paper also emphasizes the computational efficiency of the attack.
Yes. The researchers found that generating the poison samples using algorithm 2 requires minimal computation time.
So it's fast, too.
This efficiency adds to the attack's practicality,
Wow.
as it can be executed relatively quickly and easily.
So we've got an attack that is effective,
Absolutely.
stealthy, and efficient.
It highlights a critical area of concern.
It's a potent combination.
As continual learning models become more prevalent in real-world applications.
Yeah, it really underscores the need for robust defenses
Absolutely.
against these targeted data poisoning attacks.
Right. Now let's shift our focus to how the researchers quantify the severity of the attack's impact on the model's performance.
Right.
They do this by examining how the attack affects the forgetting measure for the targeted task.
Can you elaborate a little bit on what forgetting measure refers to?
The forgetting measure essentially quantifies the degree to which the model forgets previously learned information after being trained on new data.
Gotcha.
In this paper, they specifically calculate the difference in accuracy on the targeted task
Okay.
before and after the model is trained on the new task with poisoned data.
So it's a direct measurement of how much the model's performance on that task deteriorates.
Exactly. A higher forgetting measure indicates a more severe impact of the attack.
And what do their results show about the forgetting measure in relation to the poisoning rate?
The paper presents these findings in Figure 6
Okay.
across both datasets and all 3 algorithms. They observed that the forgetting measure increases
Okay.
as the percentage of poison data increases.
So the more poison data, the more the model forgets.
These findings highlight the direct correlation between the amount of poisoning
Right.
and the severity of the attack's impact on the model's ability to retain previously learned information.
This has been a really comprehensive look at the paper's experiments
It certainly has.
and results.
It raises serious concerns about the security and reliability of these models,
As does.
especially as they are being increasingly deployed in real-world applications.
Let's continue this exploration in our next segment,
Okay.
where we'll discuss potential defenses and the broader implications of these findings. Okay, so we've spent the last couple segments really unpacking this targeted data poisoning attack against continual learning models.
Yes.
And it seems like, it's a pretty significant threat.
It is. The research demonstrates a clever way to exploit the very nature of continual learning to manipulate what a model remembers and forgets.
So the researchers didn't really get into specific defense strategies in this paper,
Right.
but they did kind of hint at some potential directions for future research.
That's right. They emphasize the need for more robust and secure continual learning algorithms
Okay.
that are inherently less susceptible to these types of manipulations.
So it's like, instead of just focusing on
Just like-
how to improve the learning efficiency of these models,
Yeah.
future research should also be looking at the security and resilience against adversarial attacks.
One promising avenue is the development of algorithms that can effectively distinguish between clean and poisoned data during the training process.
So like building some kind of like immune system
That's a good analogy.
for the model to be able to
Right.
like detect and reject like harmful inputs.
Another area to explore
Yeah.
is the development of more robust weight consolidation techniques.
So can you elaborate on what weight consolidation techniques are?
Yeah, so weight consolidation techniques are central
Okay.
to regularization-based continual learning.
Okay.
They aim to protect the weights
Mm.
that are crucial for previously learned tasks
Right.
while allowing the model to adapt to new information.
Yeah.
Improving these techniques, making them more resistant to subtle manipulations like the ones we've discussed, could significantly enhance the security of these models.
So it's like we want to make sure that the model can
You see-
hold on to its
The
knowledge
goal is to create a system
and not have it be erased.
where the model can learn continuously
Right.
without being susceptible to targeted forgetting
Yeah.
induced by malicious actors.
So this research really highlights like the importance of considering security
Absolutely.
as like an integral part of continual learning model development,
As we move forward
not just an afterthought.
with deploying these models in increasingly sensitive applications,
Mhm.
their robustness against adversarial attacks becomes paramount.
It's a call to action for the research community
Well said.
to develop like new techniques and strategies
Yeah.
that ensure the trustworthiness and reliability of these
Yeah.
really powerful AI systems.
As continual learning models become more integrated into our lives,
Right?
safeguarding them from these types of attacks is crucial
Yeah.
for ensuring their safe and beneficial use.
So to kind of wrap up our deep dive today,
Yeah.
let's just briefly summarize the key findings from this research.
Certainly, the researchers successfully demonstrated the feasibility of a targeted data poisoning attack against regularization-based continual learning models. This attack induces catastrophic forgetting of specific tasks
Right.
by injecting cleverly crafted poisoned data
Yeah.
into the training process.
And they demonstrated this effectiveness
yes,
across different continual learning algorithms and data sets.
it highlights its broad applicability.
And they also talked about the attack's stealthiness.
Yes, the poisoned data is difficult to distinguish from clean data,
Right.
and the attack itself is computationally efficient,
So it's really hard to detect and prevent.
making detection and prevention a significant challenge.
So this research really serves as a wake-up call. Like,
Right.
really need to start thinking about
It's an important contribution
robust defense mechanisms to protect these
to the field of adversarial machine learning,
important AI systems.
pushing us to think critically about the security implications of continual learning
Right.
and to prioritize the development of more secure and resilient models.
Well, thank you so much for joining us on this deep dive into the world of continual learning and its vulnerabilities.
Absolutely.
We hope this has been insightful. And until next time, keep learning and keep exploring.